So some concerns for like yourself was resonance structure. So let me ask you this. I don't know if this is on here, but this would be not necessarily a resonance structure. But when we look at carbon dioxide, this is a classic example. What element is always going to go in the middle? Carbon, and if it's carbon's not present, it is what? Nitrogen. Now, when we look at, for instance, having this large molecule like H3PO4 or H2SO4, okay, when we look at those, okay, whether it's this acid, which is phosphoric, or this one, which is sulfuric, okay, which one of the elements in this compound goes in the middle? The sulfur or the phosphorus. Now, the reason we say that is because you have these four oxygens that would be going in all directions, like that, okay? So, when it comes to this carbon dioxide, we know that carbon goes in the middle, because we said it's either carbon, if that's not present, then probably nitrogen. So, as we look at this, the first step you might do is say, well, carbon's in column 4, so you might try this. And then you're going to say, well, we got one oxygen, make a single bond, and then going over here, is there a problem with this? Carbon does not have 8, neither does oxygen. So, yes? Only carbon, oxygen, sulfur, and nitrogen can double bond. Okay? Yes. And then triple bonds only occurs with 2 elements. Carbon and nitrogen. Okay, so when you look at this, okay, do you think you can see what you would or should or could do next? A single bond doesn't work, so then the next step would be well, it's sometimes that can happen, but in this case here. Now, the indication that would say that is, notice when you have your electrons split like this, and these guys are by themselves, okay? So a single bond's not working. So if we take these 2 dots for electrons for carbon, and then match it up with that single electron there, and then this one, now, does that oxygen have 8? Yes, it does. So then when we look for this carbon, it still has 2 dots left. So what do you suppose you're going to do with this oxygen then? Yeah, double bond it. You're going to do the same thing. Now, does this have a resonance structure? No. Resonance structures means that there's more than one can exist, because these exist in 3 dimensions. Okay? Your X, your Y, and pointing out at your Z. So what that means then, the example we did was ozone. And with that, then is when you're looking at O3, okay? We're going to put one oxygen here, and then we know that you're rotating a double bond. So we know at some point we're going to have a double bond here. So if we double bond an oxygen here, okay, and then do a coordinate covalent bond, can we put a double bond here like we did with CO2? You cannot. Why are you correct when you say no? Because if we put a double bond here, then we've got 10. Okay? So this oxygen has 8, this oxygen has 8, this oxygen has 8. So what that means is, as we look at that in 3 dimensions, is who's to say that this double bond is not on the other side. Okay. Exact same thing, but either the double bond is on the left or it's on the right. And that can happen with SO3, I think, is your other structure. It has a little asterisk that says resonance structures. Okay, so for instance, is as we look at SO3, okay, it would be as follows. I don't know why I erased that. I could have still used it. SO3. Does it have a charge on there too? Does it say anything about a charge? No. That means you have extra electrons. Like for instance, okay, if we did the element fluorine, we know that 1s2, 2s2, 2p5, because fluorine being a halogen is in which column? The seventh one. So when you look at either Bob or your periodic table, what does it say inside fluorine's box for a charge? -1. So what that means then is if we do the dot diagram, okay, notice we've got 7 X's there coming from these 7 electrons. Well, since it has a -1 charge, means it's gaining 1 electron, and that's why fluorine has that -1 charge. It has more electrons than it does protons. Right. So that means it's got 2 extra electrons. The whole thing does. Just SO4. Well, are we communicating here? Or?
So like SO4, like when you write it out as a thing, there's like 2 words added on.
Yes. Sure. Now I'm thinking here. How about if it's is it just the charge or is it just because it's a -2? Just the charge. Okay. So I'll even let you pick this, Tom. Look to your right. It can't be coal, all right? It can't be coal. Look to your right. Who do you want to get rid of? Okay, if I had not said that, what would you have said? Look to your right and pick who do you want to get rid of. Yeah. Okay, so now open it to anybody now. Okay, so, but, okay. Yeah, I should have classified that if you're getting rid of someone with poison. So it has to be someone in this room.
What makes poison? What element?
Well, there isn't really one element on there. Well, chlorine does, yes, but.
No, but there's a compound.
Yes, there is. Smells like, okay, so we're getting rid of Jordan. Okay. No. Okay. So when you look at that, Tom, a physical characteristic of that compound, you smell almonds? I smell almonds. So if you were a pathologist, okay, that was analyzing maybe what appears to be a victim, there's different laws throughout the U.S. that if someone, let's say, passes away from what we may believe as natural causes, if once the coroner or the pathologist perceives them, if they're under the age of 18 or under the age of 21, I think each state may have similar laws that say this person, we need to do an autopsy on them. So when this person is in front of the pathologist, one of the things they may check for, they might be able to smell almonds. Okay? Almonds is a very characteristic smell for a specific toxin or poison. That's the cyanide ion. Okay? And that's cyanide right there. So what we're getting at is, since we're saying -1, that means that this molecule has one extra what?
Electron.
One extra electron. Okay? So, for instance, when it comes to capital punishment, whether you believe in it or not, that's besides the point. We're not saying, oh, I don't believe it or I do believe in it. No. What we're getting at is, should different states for capital punishment use the cyanide? I think it's potassium cyanide. I think what that does is it might be potassium chloride, but one of them two, I think, affects the rhythm of the heartbeat and it causes that to stop. But anyway, this is a poison as well. So when you look at this compound now, or this molecule, since we have both of them present, it doesn't really matter which one you start with, but what we're going to say is, let's just go ahead and start with carbon, and what you might try to do is, okay, single bonds. There's our carbon, here's our nitrogen. That does not balance out. I mean, neither one of them have 8, okay? So single bond doesn't work. So then you're going to try, well, let's do a double bond then. Remember, when electrons are not shared, especially when you're doing multiple bonding, don't do this, okay? Keep your unshared pairs of electrons together. It's kind of like saying, keep your hands to yourself, you know, if you're sitting next to them. Yes?
Is there ever going to be one though where like you're filling it and you run out and you have like one by itself? Or is it
No.
usually not? Okay.
Nope. So this would not be the case. You would not split them apart, but what you might be thinking is, well, you did that up above. Well, we already know that doesn't work, because here you're trying to show single bonding. But when you do double bonding or multiple bonds, those electrons you do not want to separate. You'd want to keep them together. So there's our carbon. Now we would do this and notice, well, we're getting closer with carbon and nitrogen, but neither one of them have 8 electrons, do they? So in the final step, if single bond doesn't work and if double bonds don't work, then we do what? We try a triple bond, which means this. Okay, there's our triple bond. This carbon has how many electrons left? It's got 1. So we'll put him there. What about this nitrogen? Okay, don't do this. Why not? Because these are unshared pairs of electrons. Keep them together. Okay, it doesn't matter if you put both on the side or both on the top. Either one's fine. So that nitrogen now has 8. How many does that carbon have? 7. But look back to your original compound. What is it telling you? Yeah, because this is saying we have 1 extra electron. There it is. It doesn't matter if you put a dot or an X, an E. To me, I think it's always made the most sense that you put an E. Would that be incorrect if you put a dot here? Well, no. But what do you think that would be stating if you put a dot there? What do you suppose that is? That it has 5. It does not have 5. It only has 4. That's why it's always a good idea to keep separate types of shapes. For saying that still looks like a big dot yet. Okay. But you get the idea then. And when it comes to these elements that have multiple bonds, try a single. If it don't work, go to a double. If that don't work, then try a triple. But what that charge means is just telling you how many extra electrons it has in the compound. All right. Okay, so sulfur trioxide, SO3. Okay. So what that would mean then is, again, if you were to try this, okay, sulfur is going to go in the middle because we have all them oxygens rotating around. So let's try 1, 2, then you might go 3, 4, 5, okay? So now we can go ahead and attach these oxygens on here. Oh, yeah, I was seeing if anybody was paying attention. Sulfur actually has 6. So if we try that, then we put an oxygen here with a single bond. Things really aren't working out like they should, are they? And then you can say you can do that coordinate covalent bond here. This is only oxygen that's working out. Okay? But these two here are an electron short. Yes.
So is like on the side of the S where it's like dot and then X below it?
Which way am I going?
2 inches here. Right there, yeah.
Okay.
So is that saying? So is that saying with the sulfur atom or whatever it is that saying that it's on the O now, or are they like bonds?
This is a single bond. This right here, that's a single bond. That means they're sharing those two. To where sulfur's saying, that's my electron. Oxygen, no, that's my electron. That's my electron. That's mine. They just go, they share. I'm sorry, what?
This is wrong.
This right here is wrong so far. Now, one of the things that when you look at the sulfite ion, not sulfate, but sulfite, it has a -2 charge. So what would that tell you about this compound now? How many electrons is this oxygen short? 1. What about this oxygen? So sulfite actually has a -2 charge, okay? But we're not telling you that in this case. That would be another example of it has 2 extra electrons. Okay.
Again, where sulfur gives 2 electrons to oxygen, oxygen doesn't have to like double bond it or anything. They just share.
Correct. Yes. Okay, so when we're looking at this, notice we have those extra electrons up there just kind of hanging out, not doing much. Okay? So we already have established that we wanted SO3 without a -2 charge. So what that means then is let's take these away from there and do something like this. Now, you might be asking yourself, well, how are we supposed to know that? Well, I'm not really sure I have a good answer for that, other than practice. We get better at this. You might see an example like this again. So this bond is pretty simple, that coordinate covalent bond. Okay, so what might we try with one of these oxygens? Yeah, that double bond can rotate throughout the compound. So then, the next thing you might be asking yourself is, well, if this oxygen double bonded, well, why can't we do this here? What's that telling you? Okay? Right. So that's telling you that's not correct. So then, what would you do with these 2 X's then? Them to the outside, and then what that means as far as resonance structure, here you got it on the right. maybe flip-flop the two, put the double bond over here, single bond there, and coordinate covalent bonds on the right and on the bottom, and a double bond over here. Yes. Yes. Yep. Yep. So this would be a resonance structure, and then put your oxygen down here. I know I just did that really quickly. I know you're not supposed to do that, but now you get the general idea. Yes.
So why can't the three oxygen and then having the sulfur just transfer their atoms or whatever they are to the oxygen and that switches them on?
If I'm interpreting your question correctly, what you're saying is why can't there be like an oxygen down here, like this?
No. Yeah, that's what I'm saying.
It has too many to do that, because metals, remember, metals give away electrons. Non-metals do not. There's just too many to try to, let's say, I guess what pops in my mind is just think of a grate in your sink, and you're trying to when you wash your dishes, maybe there's some leftover hamburger crumbs or something like that the grate in the bottom of your sink catches, but you're just trying to push them through just to get them down the drain. Well, that's kind of like how I would interpret this sulfur. It can't just start pushing all those 6 electrons out of its outer energy level. There's just too many to do that. Kind of like trying to push all the molecules or substance through that grate. It just can't. Okay. I don't know if that's a very good answer, but when you think back to, what was it, spooky action, or no, it was Einstein's spooky action, and then Niels Bohr's, I can't remember what his theory was. But from that video, the professor, I think from MIT, just said, that's just the way we have to accept that that's how this is. Same thing here. You just have to accept that that's just how this is. Yes?
Okay, so for like this one, I think I did this wrong because I thought like it's just what's on the outside, but like this couldn't work because the chloride would have too many atoms, right? Have too many of these.
Okay, but then remember, when you do this, chlorine cannot double bond. So what do you think you would do?
So I would do that, boom, and then they'd have 6, and then my extra electron is over here.
Yep.
With oxygen. Okay.
Yes.
So I think I have those for you. So it has the middle one has to have 8. It cannot have more. Right?
Correct. Correct. Okay, we'll pick up with this tomorrow. I will not be here. Of course, you'll have a substitute. You can work on these papers or something else. Just don't cause any problems. I know you won't. So pick up with this on Thursday.